As we all know, for solid state control of drives, as the name suggests, solid state control. The solid state control is nothing but there the power electronics. We have to know the basics of power electronics. So today, now in the first session, we'll just go through the basics of power electronics, and then the next session we'll go to the drives. So first of all, coming to power electronics, as you all know, what is the basic difference between power electronics and linear electronics? You would have come across a diode, is it? A power diode and even a linear diode. So what is the basic difference? Anyone? What is the basic difference of a power electronics device and a linear electronic device? Its power handling capability is more, yeah, yes, then accurate.
High frequency, dealing with power plus dealing with high frequency.
Okay, for high frequency applications, you're saying we go for power electronics device. Anything else? So now we can see this. So how is power electronics distinct from linear electronics? First of all, power electronics, if you see, can divide into two portions. One is power engineering, next slide, power engineering, and one is electronics engineering. So here, power engineering, in power engineering, we deal with high power level, and in electronics engineering, it is low power level, that is signal level, you can say. So for high power level, in the sense, it will be of kilovolts, okay, and the voltage will be of high kilovolts, and the amps also, it is in the 5000 amps or higher amps. Okay, so 10 kV, you can say that 10 kV voltage and around 5 amps. And in linear electronics, it will be only few millivolts or few milliamps. Okay, so that is a major difference. That is high power level. Next is high efficiency, and efficiency is like high efficiency in case of power engineering. Efficiency is a very major concern in power engineering, but in electronics engineering, if you see, their efficiency is not a major concern. In power engineering, mainly what we do, generation, transmission, and then distribution. So their efficiency is a very important parameter. But in case of electronics engineering, there you get signals and transmit the signals, and you receive the signals, where these signals are we have to get these signals distortion less, but efficiency is not a major concern there. Next is high. Next thing is high. Next is electromagnetic interference. Sorry, what is the basic principle in power engineering? In power engineering, if you take a motor or generator, the basic principle there is the basic principle is electromagnetic induction. So that is the third point. You can see that it is electromagnetic induction. But in case of electronics engineering, mainly there are vacuum tubes or some gas filled tubes. Or that principle, or nowadays you go for semiconductors. So it is the movement of holes and electrons are the basic principle in electronic engineering. So these are the major difference between power engineering and the electronics engineering. Okay, so this is the main thing. Next, if you see an ordinary diode, this is an ordinary diode. It has a p-type holes and an n-type region with electrons, and a battery is being connected. You can see here. How is this diode, which is a linear diode, which has a capability of standing some few volts and few amps? How is it able to carry very high voltage and current? What is the principle there? How can we make it as a power diode? How can we make it as a power diode? Anyone from the center? Which is Chandigarh center? Okay, an ordinary diode is there. How can we make it a power diode?
For increasing the width of the depletion.
Increasing the width of the depletion. How will you increase the width of the yeah, by increasing the doping level, by changing the doping level. So the ordinary diode, when you automatically what will happen, it will be able to withstand high voltage and high current. Okay, so now we have to change the doping level. So you all know what is doping and all. So you mainly, we go for here semiconductor devices. The semiconductor devices will be silicon, germanium. So they are silicon. If you take, the valency band is 4. Now how will you dope it? Doping is adding impurities to it. So you can add a trivalent impurity or a pentavalent impurity. If you add a trivalent, so they say I'll be showing that. So here this is the doping. Here germanium is taken with 4 valency electrons and boron is, so boron is added to germanium, and here boron is having 3 valency electrons, and you can see one hole is left when it is linked with the side nearby matrix. You can see one of the hole is left there. So holes are formed there. So here you can say this is a p-type material now. And when the number of holes increases, what automatically what will happen? The doping level is also increasing. So you can have p-type, you can have p plus or p minus also. Similarly, you can have a n-type material. How can we do it? We have to add pentavalent elements into it. So pentavalent element is, here say phosphorus added and one extra electrons it has, and now it becomes a pentavalent. So this is how, by doping, by adding impurities, we can make an ordinary diode carry high voltage and high current. So here next slide you can see power, it's a power diode. So here what they have done in order to make an ordinary diode and a power diode, as we already said, they have added a like extra doping is being done here, and one N minus layer is being introduced. Because of this N minus layer, this diode can carry high voltage and high current. So what happens because of this N minus layer there between the P plus and N plus region, the depletion layer width will increase. Initially a P plus and P and N region is there, a small depletion layer is there. But because of this N minus layer, the depletion layer will increase because of the N minus, it spreads into the N minus and goes slightly into the P plus. So that region N minus is nothing but the drift region. So thickness of the drift region will give what is the voltage it can withstand. Okay, can you get it? So if the drift region, like if the thickness is more, it can withstand more voltage. If the thickness is less of the depletion layer, sorry, of the drift region, automatically it can handle only less power. So here the P plus region, which you can see, that is connected to the anode. Here that thickness is around 10 micrometer. 10 mu mm, so micro millimeter it is, sorry, micrometer, 10 micrometer. And N plus region, the N plus region which you see at the bottom, it is 250 micrometer. Okay, so now central region, N minus epitaxial electrons and N minus region will give you what is the thickness all the nodal centers are hearing. Can I continue? You're hearing now, all of that?
Yeah.
Okay, now you can start. Start the PPT. So here you can see that is how this ordinary diode is made to carry high power. This is a simple, in order to tell you the basic principle, I took a diode. We have number of thyristors. Thyristor is a family where you have number of devices under it. We will be seeing one by one now. Okay, so this is a power diode, and I think all of you understood how to make an ordinary diode into a power diode. That is by just doping, changing the doping level, it will be able to carry high voltage. When it will be able to carry high current, say now I told you, when this drift region thickness is increased, it can withstand high voltage. But when is it able to carry high current? For carrying high current, what is required? When it has to carry high current, area of the thickness of this device, it just increase. Okay, around say 5 centimeter, or some even for carrying 5000 amps, you have 5 meter dia wala thyristors. Okay, so in order to carry very high current, you have to just increase the diameter of the device. So this is how we can increase the voltage and current. Next is charge density. So I was telling you about the charge density P plus N, we change the doping level. So if it is a P plus region and a N minus region, the thickness, that is the depletion layer, will be of more thick, and you can withstand more voltage than a P plus and a N region. So when the doping level is more between two region, it can withstand high voltage. So you can see what are the different doping levels. One is, say, in case of semiconductor. And why do we go for semiconductor? Why not metals or insulator? Okay, that is also a question, is it? So in case of metals, if you see, for example, if you take metal like copper or silver, the electron density, the free electron density there is 10 to the power 23 per cubic centimeter. It is almost filled with electrons, where no control is possible. Once your power is given, it starts conducting. That is a metal. But in case of an insulator, if you see, which free electron density centimeter. Okay. So in case of, say, backlight or some insulator, if you take, it is 10 to the power 3. There is no electrons, and you cannot add more electrons also. It will be less than 10 to the power minus 3. So there also there is no possibility for changing. The doping cannot be done there. So then the best thing is semiconductor. The semiconductor, it has a range of electrons. Electrons, or the holes and electrons, can be, by doping, can be changed. It can be changed a range of 10 to the power 8 to 10 to the power 19 per cubic centimeter. Okay, 10 to the power 8 to 10 to the power 19 per cubic centimeter can be changed. That is by doping. So that is what is shown. If it is a P plus region with more number of holes, then the concentration is 10 to the power 19 per cubic centimeter of holes, free holes there. Free electrons, that is N plus region, it is 10 to the power 19 per cubic centimeter. And similarly, if it is a P minus for holes or N minus for electrons, it is 10 to the power 14 per cubic centimeter. Holes and electron concentration. If you take only P or a N, then it is 10 to the power 17 per cubic centimeter. So by changing the free charge density there, the region P plus, N minus, P, all these things can be introduced. So is it clear? So this is how we go into power electronic device. From ordinary electronic device, this is the difference between power electronics and ordinary electronics device. So next, you can see here power semiconductor devices. First, when you say power electronics, we have generally seen the principle, and next is the devices. There are number of devices that has been classified and shown here. Next to the devices, you have circuits. Using these devices, when they are connected in a particular format, you can form some circuits. So using these devices, you can form a DC to DC converter, that is said to be a chopper, where DC can be stepped up or stepped down. You can have a rectifier, AC to DC conversion, AC supply. Okay, that all these things can be done with these devices. Next, AC to AC. AC supply can again be converted to AC, where the frequency can be changed or the magnitude can be changed. So if you want to change the frequency, you go for cycloconverter. If you want to change the magnitude, you go for AC voltage controller. Okay, so that is also possible. Or one more circuit you can make with these devices, that is DC to AC conversion. DC current can be converted into AC current. That is with an inverter. Okay, with them. So with all these devices, you can make the drive in order to structure. So next we are going to the devices. Main is thyristors, and in for control of drives, you go for IGBTs, MOSFETs. All those devices are also used. We'll be seeing step by step. So coming to the power semiconductor devices. Power semiconductor devices can be classified into two. One is uncontrolled device, another is controlled device. What is uncontrolled device? Uncontrolled device in the sense that cannot be controlled, just like a diode. Okay, once it is given a bias or once it is turned on, it remains on, or when you remove the bias, it remains off. You cannot control it in between. That is an uncontrolled device. So example is a rectifier, and rectifier circuit that you have power silicon diodes, you have FRED, that is fast recovery diodes, and Schottky diodes. All these are the diodes. Then you have some accessories like diac. That is diac is a diode like thing which can be acted for AC supply, like bidirectional. Okay, and then you have Zener diodes, then metal oxide barriers. All these are the accessories All these devices cannot be controlled. It can just be turned on or turned off. You can see that all these devices which we have seen here is just switches. What is the difference between this switch and the other switch manually what we use here? These switches are power electronic switches, and these are said to be, they are solid state switches and they are said to be static switches. Okay, they have no moving parts. The manual switch or the relay or anything we take, there are some manual movements. Here there is no manual movement. These are said to be the static switches. These power electronic devices which we see are static switches. So you have again uncontrolled. Next is the controlled. Many times in more drives and all, we require control. We require a control there. So we go for control devices. They are again classified into regenerative, non. So what is regenerative? They are the device like SCRs, track and GTOs. And non-regeneratives are BJT, MOSFET, IGBT. And what is the difference between regenerative and non-regenerative? Regenerative is, yeah, say for SCR, you give a gate pulse to the SCR. SCR, you all know, it has just like a diode with a gate terminal there. It has an anode and a cathode and a gate terminal. Now, if you give a gate pulse, it gets turned on. Once it is turned on, even if you remove the gate pulse, it goes on conduction. It will go on continuous conduction. Okay, is it clear? When we give gate pulse and if it is going continuously in conduction, we say it is regenerative. For example, if you take in SCR, there are two thyristors connected in anti-parallel. When those two thyristors, like Darlington pair, we say, when they are conducting, they will continuously go on conduction. Okay, so that is about SCR. But in case of a MOSFET or IGBT, once you remove the bias, automatically they will get turned on. They are said to be non-regenerative. They are not regenerative type. And then integrated circuits are also there. Integrated one is IGCT, that is an integrated gate commutation thyristor. Peak power integrated circuits are there, and intelligent power modules. These are all integrated circuits. ICs, guys, format you get. These are integrated circuits. Next is here you can see a chart where power switches and their ratings are given. So there are different types of power switches. You have MOSFETs, IGBTs, GTOs, then thyristors. So for high speed application or high frequency, for high frequency application, which one you go? MOSFET. So low rating, and if it is if you want it for low rating and for high frequency application, you go for MOSFET. Next is you can even go for IGBTs. But for applications where you want very high voltage and current, like high power you're dealing and frequency is very less. Say for example fax, flexible AC transmission. They are very high voltage, around 10 kV and 5000 amps have to be handled. Then you go for thyristors, okay, where frequency is 50 hertz or 60 hertz. Okay, so there in that place you can go for thyristors. That is the power ratings which is given. So next here you can see the power rating versus voltage rating is given. So for motor drives, again you can see voltage around some 7 kV that you have motor drives, and the power rating is also given. Similarly for the other application, traction and fax are given there. So this devices which you use, again we saw the same thing is given here. MOSFETs is for very high switching frequency, IGBT and SCRs are given. The same thing what we saw in the last slide. Next we see some real-time devices. So you have number of companies producing it. You have Mitsubishi, UPEC, ABB. These are some of the common companies which are generating these devices. So Thyristor, say you can see at 12 kV, 2360 amps Thyristor, which is being generated, which is being produced by, which are generating this devices. Okay, so different devices are being shown here. And this is a table, characteristics and symbol of different devices are given. So almost we all know this, a diode and its characteristics is given, a thyristor, its symbol is given and its characteristics. Then you have a static induction thyristor, SITH, the symbol is given, GTO, gate turn off thyristor. Then you have MCT, that is MOS control thyristor, MTO, that is most turn-off thyristor, ETO, emitter turn-off. So these are some of the power electronic devices which are present. You have IGCT, that is integrated gate commutation thyristor. TRIAC is there. Then you have light activated SCR, LASCR. Then PNP, BJT. So these are the characteristics, and it's in IGBT, a MOSFET, and you have a static induction transistor. So these are some of the devices which we use in the power electronic devices. So next, as I already told you, with all these devices, next step is we make circuits. The circuits are DC to AC converters or DC to DC converters, AC to DC converters or a AC to AC converter. So that is what is shown here. So again the same thing as I told you, DC to DC converter is a chopper, DC to AC converter is an inverter, AC to DC converter is a rectifier, and AC to AC converter is a cycloconverter. So next is a thyristor. So all of us know thyristor is one of the, like here the symbol which is shown is for an SCR. Thyristor is a general family name. Any device which has more than three terminals, more than three junctions, okay, PN junction, more than three PN junctions, and they have different concentration, doping levels, then they are said to be a thyristor. Any semiconductor device which has more than more than three junctions, they are said to be a thyristor here. Okay, so here this is an SCR. SCR is the first thyristor which was introduced in 1956 in the Bell Laboratory. Okay, so here this thyristor is having, so here they have shown a thyristor with P, N minus, P and N plus region. It depends on the manufacturer. Sometimes you can even have a P plus, N minus, P and N plus region. So different manufacturers give different types of structures. So here this you can see here, this is an anode, a cathode and a gate. Okay, and you have three junctions here. So these are the three junctions. Okay, so this is being shown here. And steady state characteristics of a thyristor. Next we go to the steady state characteristics of a thyristor. So a thyristor, if you see, there are three regions. One is forward blocking state. Forward blocking state is shown here. This region is the forward blocking state. Okay, forward conduction. This region is said to be the forward conduction. Okay, and this is the reverse blocking. The reverse blocking is shown here. This is the reverse blocking. So there are three states. In forward blocking, this forward blocking, now you're not giving any gate pulse, just you're going on increasing the voltage. What will happen? It will not go into conduction. But at one particular voltage, that is this point, it is said to be the forward breakover voltage. Beyond this voltage, if you go on increasing voltage, the thyristor will break down, sometimes get damaged. Okay, so we should not increase our voltage beyond this point. But before this, say at any point when you give a gate pulse, if you give more gate pulse, it will get turned on faster than previous. So now say you are giving a more gate pulse, that is IG4, which is greater than IG3. So here itself it will go into conduction, and this is the conduction state. And conduction also, you can see there is a small voltage drop. This voltage drop, around 1 to 2 volts voltage drop, will be that is due to the ohmic resistance. Ohmic resistance, because of the ohmic resistance, you have some voltage drop. And this is the reverse blocking state. When you keep the anode cathode junction in the reverse bias, the thyristor will be reverse bias, and still again you go on increasing the voltage across it one particular point, and this avalanche breakdown, the current will start increasing rapidly here. The current will start increasing rapidly. But if you have connected some load, this will not go parallel to this IA armature, the anode current. It will not go parallel to it. Slightly the curve will be towards this anode current, like this. It will be slightly towards the anode current. Okay, so that is what you can see here. This is the steady state characteristic. So mainly when you operate a thyristor, we operate in two regions. One is off or the on. So when it is off, we will be keeping in the forward blocking state. Even the reverse blocking you can keep, but mostly we keep it in the forward blocking state. When you go into conduction, we keep it in this state. This one here, which you can see here. Okay, this is for conduction. Next is the gate characteristics of a thyristor. Here you can see the gate characteristics. And when you take a gate characteristics, it is just like a diode. Say the gate and the cathode junction is just like a diode. So the diode characteristics only you will have that. And here there are two characteristics you can see. See, one is this characteristics which I am showing here. One is this one, and the other one is this. So this is the minimum characteristics of the gate. Minimum characteristics in the sense the gate should have at least this characteristics. Below this, the gate will not turn on the thyristor. And another one more characteristics is there, this one which you can see where the S2 is there, this line, BC line. In that BC line, this is the maximum characteristics. Beyond that, the thyristor may get damaged, so you should not give more gate current also. Okay, so the gate circuit which we are choosing should lie between these two regions. This region which you see here and with this region, the characteristic should lie between these two. Okay, and now say the load characteristics is drawn. The load is nothing but say open circuit voltage of this you take, and this E you will get, and similarly shorted and short circuit current you get a point here. This point. This is the short circuit point below. This is the short circuit point, and this is the open circuit point here. Okay, so join that. That is the load line. Okay, so if our characteristics is between these two, say for example, let me take a curve like this. In between, if you take a curve like this, the point at which it joins with this line, that is the operating point of the thyristor. Okay, the gate circuit operates at this particular point. And here you can see one thing is, say this Ig max. Here you can see in the characteristics in Ig max, this is the maximum current which can be given. Beyond that, the current will be damaged. And similarly, this Vg max, this is the maximum voltage which you can give. Beyond that voltage, the thyristor will be damaged. Similarly, minimum is also given, Vg minimum. This is the minimum voltage which has to be given in order to turn on the thyristor. And similarly, Ig minimum is the minimum current corresponding to it, where that current has to be required. But you can see one more term here, Vng. Can you see that? This Vng. This is required. This usually the manufacturers give one more minimum value. That is a value below which most of our interfacing, like say, or some noise signal, or say the nearby thyristor is getting turned on, that will produce some disturbance. All those voltages or all those signal level should be below this voltage level, Vng. Okay. Otherwise, false triggering may occur due to the nearby circuit. This will again get turned on. So this is the gate characteristics. Next is switching characteristics. So this is the turn on characteristics which you can see. Similarly, this is the turn off characteristics. The combined characteristics is shown here. This is the gate turn on and turn off characteristics combinedly it is shown. So whenever you turn on a thyristor, it goes into conduction. Okay, we saw the forward blocking state and the conduction state. So from this step, forward blocking to forward conduction, it takes little time. So that time is said to be the turn on time. So here you can see which is T on. T on is shown here, that is the turn on time, and this T on can be divided to three regions. One is the delay time, rise time, and the spread time, TP. So three regions. So delay time you can explain as it is the time taken for the anode voltage to fall from the maximum value to 0.9 of the anode voltage, or it is a time taken for the anode current to rise from its minimum leakage current to 0.1 of its armature current. It can also be said as the time required for the gate current to rise from 0.9 to its maximum value. This is shown here. Okay, so these are the things. And next is the rise time. Rise time is the time taken for the anode current to rise from 0.1 IA. This is shown here. Say 0.1 IA to 0.9 IA. So that time is said to be the rise time. So here even the delay time and the rise time can be increased by increasing the magnitude of the gate current. Gate current magnitude is increased automatically. This time will be shortened. So the thyristor can be turned on faster. And here you can see that this is the spread time. Spread time is the time taken for the anode current to rise from 0.9 A to the maximum value, and similarly it is the time taken for the anode voltage to fall from 0.1 to its minimum. That is the on state voltage drop across the thyristor, that region. And here you can see all the three. The loss is more in the rise time region. When the rise time, this region, the losses are more. So we have to try to keep that loss as minimum as possible. Okay, next thing is, if you see, this is the commutation. When the thyristor is turned off, then it will take little time for the thyristor to come to the off stage. So that time is said to be the turn off time. So once the commutation circuit starts, the current will start falling, and the time from which the current falls to zero at T1, so it is shown here. The time it reaches zero to the time it completely like after recovery again it becomes zero. So that time is said to be the turn off time. So here turn off time is represented by TQ. TQ is the reverse recovery time plus the gate recovery time. So the reverse recovery time starts from T1 to this T3. That is the reverse recovery time. So reverse recovery time, you can say T1 to T2. The slope follows the same slope of the commutation cycle. Di by dt, the slope, and it will follow the same thing. And that region, what is actually happening is, inside these thyristors, when it is turned off, there are a lot of charges present there. Okay, like lot of charges are locked inside that. So first of all, we have to flush out all those charges, extra charges which are present there. That is the region between T1 and T2. Around 60% of the charges are flushed out. After that, again, if you see, there are some more charges which has to be flushed out. That is flushed out at a slower rate. That depends on the inductive property of the circuit. Okay, so depending on the inductive property di by dt, slightly slope is deeper. It flushes out at a faster rate. From T3 to T4, that is a time where the charges which are locked in the junction, in the junction, there will be some of the charges present. Those charges cannot be flushed out. They have to undergo recombination. After recombination, they will automatically get removed. So that is a region, that is TGR. You can see here T3 to T4. That region is nothing but the gate recovery time. But overall, if you see, the circuit will not get turned off at T4 also. It depends on the circuit, the full circuit to which you have connected this thyristor, overall circuit. So that is the thyristor circuit turn off time, TC. Circuit will also take some time to turn off. Depending on the circuit also, the thyristor will take some time to turn off. That is the overall TC time thing. And here you can see from T2 to T3, when there was a sudden drop in charges, like charges are flushed out at a faster rate, there is a dip in voltage. So this side already told you, it is because of the inductor which is connected to the circuit. Okay, you can see that for di by dt protection, sudden rate of change of current is there, the device will be damaged. So we put an inductor there to limit the current di by dt, that I will be showing you later. So because of that inductance, this peak reverse voltage is there. So you have to choose that inductor also in a proper value. Otherwise, what will happen? A very deep voltage drop will be there. Voltage spike will be there and it will damage your device. That is also a major concern. So this is the characteristics of a thyristor. So whenever you speak about a thyristor, it is very simple. We draw the circuit and we leave it. But actually, there are a number of other circuits also connected to this thyristor. Like you have a firing circuit connected to this thyristor, you have a commutation circuit connected to the thyristor, and even you have protection circuits connected to the thyristor. Okay, all these circuits together form our overall thyristor. Okay, it is not only in case of thyristor, like all types of thyristors, even in MOSFETs and all, you have firing circuits, you have protection circuits, but there, like commutation circuits, the commutation of circuit also depends on what type of supply we are using. So one by one we'll be seeing. So thyristor firing circuits. So thyristor's firing circuit, if you see, there are before analog circuits were used, but nowadays if you see, in the place of analog circuits, digital circuits are used. Okay, there are a number of digital circuits which can be used for this firing purpose. Can you say some of the things? I just want it from the center. Are they listening? We'll know, no? So from the centers, any center? And are you all listening? One of the center, you can just connect with center. To St. Joseph College, you connect. St. Joseph College.
Ma'am.
Are you there?
Yes.
Can you say any digital circuit that can? Any Any idea?
Pardon, ma'am.
Any digital circuit which can be used for firing. Say analog, you can use RC firing, you can use UJT firing or pulse transformer for firing. Can you say any digital circuit that can be used for firing? Any idea? Anyone? No one?
Sorry, ma'am.
No. Next center, can you send connect next center? Guys, can you say any digital circuit that can be connected? Let it be. Sunrise groups. Okay, there are many controllers here from NITTTR center. What are the controllers? पता नहीं है. Yeah, D space board, FPGA board. Adrenos. What are Adrenos actually? They are microcontrollers actually. So best is microcontroller. All of you would have come across that, is it? So microcontroller, if you see, that is the best digital controller. You write a program, you give a delay there, and call that delay and make a particular pin high. So that thyristor which is connected to that will get turned on. Okay, is it clear? So microcontrollers, if you high speed. Okay, the FPGA boards are little high speed than the microcontroller. Because in FPGA boards, if you see, it is the thyristors, the transistor logic. It is the hardware which is going and which is burnt inside the chip. It is not the software, the program what we are writing. When you write a program and you call, what will happen? It will call the program has to run, and there is a delay time. So the timing to fire it will, some delay will be there. So for applications where very high speed application is required, you go for FPGAs. Example, say your car, and you're driving a car and suddenly you meet with an accident, and you can see that an air balloon will open, not to protect. In that place, you go for microcontroller, what will happen? By the time the air balloon opens, the person would have died. So there you can go for a FPGA. So FPGA is a little costly. So, but when you go for a high-end cars, you can go for cost is not a major concern there. So in FPGA, it is the hardware. Like when you program it, it is the thyristor logic or the flip-flops that is being burnt into the chip. Okay, so what will happen? That chip is now a hardware. Hardware is running, which will be faster than the microcontroller. Even you have another many other options. Two of the options we'll be seeing in the course itself. One is a MATLAB. Nowadays we all use MATLAB. That's a software. But this software, when it wants to, it should be connected to the hardware. You require data acquisition codes are required. Data acquisition code is DSpace, which is easily interfaceable with MATLAB or Arduino boards, as you said. Arduino is also a microcontroller only. So microcontroller boards can be kept that can be easily connected. Similarly, LabVIEW and NILVIS can be connected to it. And NILVIS, when it is connected to the hardware, programming you have done and you have connected to it, can be connected. Connected to your hardware, That is also a form where you can control the drives using digital control. So all these are digital controls, and nowadays we don't go for these analog controls. We go for digital because they are more reliable, they are more fast, they are more efficient. Okay, and even say if you want to remove harmonics and all these digital filters, the firing angle can be adjusted, and you can do it. So digital filters are preferred these days. So again, we'll go into a presentation. You have a thyristor firing circuit. Some of the conventional firing circuits are shown here. One is thyristor firing circuit. Many way you can fire the thyristor. One is forward voltage triggering. You don't do this. Say you are going on increasing the forward voltage, and it will go into conduction. But this is not preferable. Sometimes the device may get damaged. Then dV by dt, sudden rate of change of voltage. Again, thyristor will be triggered. Temperature. When you change the temperature, you automatically it will get triggered. Light triggering. In the notch, the thyristor, you give a notch there in the gate portion, and you make particular wavelength light to fall on this notch using some optical fibers. So automatically what will happen? The gate will get turned on. So this gate signal with this light signal, that combination can also be done. Then is the gate triggering. So most preferable is gate triggering. Next, coming to the gate triggering for analog circuit, there are many. Some of the things are listed here. You have R circuit, RC firing circuit, UJT firing, and pulse transformers in firing circuit. These are some of the circuits. But these resistance RC circuit and all, nowadays it is not used. Okay, the pulse which is generated also, power loss is there because it is continuous. It is not spikes. In UJT, if you see, you can get some spikes there. So power loss is less. But R and RC is not preferable nowadays. But anyway, we need to know the basic concepts. We have shown here a simple resistance resistance and an RC circuit is shown here. For resistive circuit, you can see here one variable 1 mega ohm resistance is put here, and when this resistance is changed, automatically the voltage across this gate cathode junction will change. When the voltage for breakdown of the like in order to trigger turn on the thyristor is reached, automatically the thyristor will go into conduction. So here you go on changing the resistance, automatically once the voltage is reached, this will go into conduction. But one of the disadvantage of this R circuit is R firing is only 0 to 90 degrees firing is possible. So next we go for RC circuit. So this is the RC circuit given here. 180 degrees firing is possible in case of RC circuit. Here also you have a resistance. You go on changing the resistance, and when the capacitor voltage becomes equal to the triggering voltage, automatically the thyristor will be triggered. I'm not going into depth because this is UJT triggering. The UJT triggering, one of the UJT is shown here, which has a base N region which is lightly doped, and you have an emitter region. The emitter region is heavily doped P region. Okay, and its equivalent circuit is shown here, and the resistance RB1 is between this central node and B1, and resistance RB2 is between B2 and this central node. And here eta is nothing but RB1 divided by RB1 plus RB2. This is said to be the intrinsic standoff ratio, intrinsic standoff ratio, and this is nothing but the value ranges between 0.5 to 0.8. Okay, the intrinsic standoff ratio stands with the value is between 0.5 to 0.8. So here, this UJT, its characteristics is such that here, say this voltage which you apply here, let us keep it as VE. If this voltage, when we go on increasing, okay, when this voltage VE, here the voltage is VE, and here eta VBB is the voltage across RB1. RB1, the voltage is eta VBB, and let the input voltage what we are giving is VE. When this VE voltage, then VE voltage is less than this eta VBB. Less than this eta VBB, what will happen is the negative current is negative. You can see in this region. Now what I am doing, VE voltage or the VP voltage what is given here, I am going on increasing. When I increase this voltage and when that voltage become more than this eta VBB. When the VP voltage which you are giving in here is going more than this eta VBB, automatically the, here I said the P region is heavily doped, is it? So more number of holes will be pushed into the lightly doped N region. So when the lightly doped N region has less number of electrons, so holes which are injected gets recombined with the electrons in the lightly doped region. So now more holes are there. More holes from the P region, which is heavily doped, is injected into the N region. Can you get it? So when, what will happen at one particular point, at this instant, when more holes are injected into this N region, the resistance of this so here you can see when more holes, here the P region was that which was heavily doped. When more holes are injected inside the N region में जो electrons है, that will recombine with the holes, and only less electrons were there, they have recombined, now more holes are there. So as a result, what will happen? The resistance, this RB1 resistance which you can see here, the resistance value will decrease. When resistance value decreases, automatically what will happen? The voltage will drop and the current is increasing. There is a negative resistance which is shown here in this case. Negative resistance region is formed. So this negative resistance region can be utilized by us for firing the thyristor. Okay, and after a particular, this will go on increasing. In one particular point, the resistance will come to such a point that there a saturation will occur. Below that, the voltage will not drop, and after that, the voltage will slightly increase like this. Okay, so this is so this negative resistance region. Here, this is the negative resistance region. The next slide, you can see see BCE. Next slide, sir. Next slide. Here in the BCE, here you can see this is the region. This grouping region is the negative resistance region in case of a UJT. Okay, so across this comes across BCE point. This point, 47 ohms, across 47 ohms, we can take out this voltage. Okay, using a 1:1 transformer, you can take it and you can fire a thyristor. Okay, so here you can see that the frequency at which this pulse log 1 divided by 1 minus eta. So this formula the frequency at which we require the pulse width. And what is the pulse width? So you can see here the pulse width. What is the pulse width which is required by the grouping lines here? This is the RC constant. So the RC value what you choose, that will give what is the slope of this, and that will give you the width of this pulse. So this is the pulse, and the frequency at which the pulse is required can be adjusted by our electrical circuit voltage. We are not going to these analog, but you have to know the basic principles how these are all done. Using pulse transformer, 1:1 transformer, and isolation can be given, and that is also the pulse transformer. Using pulse transformer also, you can fire the thyristor. Pulse transformer, anyway, it should have a firing circuit at one end. This pulse transformer will just give you isolation. You should know this always when you go use a firing circuit, that has to be isolated from the power circuit. You know what is a power circuit? हमने जो एक motor है, one motor is there, and you have a converter circuit. It may be a DC to DC converter, it may be a AC to DC converter, or any type of converter. When you connect it to the motor, okay, that is the power circuit there. The motor and the converter circuit is said to be the power circuit. And the control circuit is maybe an analog or a digital control. Amps. It's a very less voltage circuit, and the power circuit, it is 440 volts and high amps, 10 amps, 20 amps, I say. So these two circuits has to be decoupled. It cannot be, it has to be isolated from each other. Okay, it has to be isolated. For that purpose, you go for optocouplers. Optocouplers, what it does, it gives an optical isolation. When light falls on a transistor, say you have a diode, light emitting diode, which falls on a transistor, that circuit gets coupled. So you should have amplification as well as isolation. That is very important in case of the firing circuits. Okay, firing circuit is required. Even you have ICs, driver ICs for this purpose. Driver ICs are also present. These are driver ICs automatically provide amplification of the gate circuit as well as isolation. Okay, so this is our triac firing circuit is shown. Same way, triac also with the diac it is being fired. As similar RC circuit which we saw, the same circuit is shown here also. So I'm just skipping. And these are many other devices which can be used for firing. You have UJTs, you have PUTs, the SUS, there is programmable unijunction transistors, silicon unilateral switch, SCS, SBS, STS, diac, STC. These are the different devices that can be used for firing. Okay, so next we are going to thyristor protection circuit. So as I already told you, if you take a thyristor which is used for firing the, which is used for controlling the drive, not only the thyristor is there, you have a firing circuit which we saw. It may be digital firing or analog firing. Digital firing we will be doing in the MATLAB session, and even the hardware when we connect you will know it automatically. That is digital firing. Or analog circuits like RC circuits and all these UJT circuits you can do it. That one circuit is there. Next is protection. The device has to be protected. So for that protection we have, like say one by one we'll see, you have snubber circuits. Over voltage protection is required, over current protection is required, and gate protection is heated up. So in order to remove this heat, you use heat sink here. Okay, heat sinks are used in order to remove these heat. Next is for over voltage protection. For over voltage protection, we use snubber circuit. Snubber circuit is shown here. That is for over voltage protection. So now say a sudden voltage is given to this thyristor. What will happen? A high voltage comes across the thyristor and thyristor may get damaged. For this purpose, what we do, we put a capacitor parallel to this thyristor. First remove this resistor. Don't think about the resistor, only a capacitor is required for this purpose. So we put a capacitor in parallel with the thyristor. So what will happen? How will this thyristor as a capacitor act initially when you turn on the supply? How will this capacitor act? It acts like a short. Very good. It acts like a short. So when it is short, what is the voltage across the thyristor? Zero voltage. As you said, it is zero voltage. So now what will happen? The capacitor will start charging. It will start developing voltage across it. So automatically what will happen? Thyristor across also voltage will start developing. So from 0 volts, 220 volts or 440 jo bhi chahiye, it will be developed across the thyristor. So at once it is not happening, it is gradually. But why we are putting a resistor there? We can see here an RS resistor put there. What is the reason for putting this resistor?
Limiting the current.
Yeah, for limiting the capacitor current. Now if one say, now the thyristor is forward biased, it's not conducting. Now you give a gate pulse to the thyristor, what will happen? It starts conducting. Once it conducts, the capacitor will start discharging to the thyristor, and the thyristor will get, like, very high current will start flow through the thyristor, and thyristor may get damaged. Now to avoid that, we put here a RS resistor here it is put. You have to suitably choose what is the resistance value and you have to put across this. So this is how dV by dt protection, high voltage protection is given, sudden change in voltage. So how is this voltage, over voltage, what are the reasons it occurs? Any idea what are the reason why this voltage is like sudden change in voltage is occurring? Externally it may occur or even internally it occurs. Internally is due to, I show you the characteristics. When you're going to turn off, because of the inductor present in the circuit, one dip was there in the switch off characteristics. Did you see that? So that is because of this inductor. This is a di by dt protection we have put here an inductor. Can you see this in the circuit? Next to the snubber circuit you can see here an L circuit there. L in the circuit, that is for di by dt protection. So this causes a internal voltage spike that may damage, or externally say due to lightning there may be, or say you have connected a because most of the converters it will be connected to a transformer at the input end. So when the transformer primary is energized or de-energized, voltage spikes can occur there. That also can damage the thyristor. In order to avoid all these things, we go for snubber circuit. For any thyristor, when you do the hardware, you have to connect a snubber circuit. Next is crowbar protection for overcurrent protection. Okay, so here a crowbar short circuits this overall power converter. That is, when this thyristor, crowbar thyristor is shorted, what will happen? This is bypass. This power converter will get bypassed. So initially say the circuit is operating properly. Now in case the power converter is drawing very high current, what will happen? Current sensing resistor will carry high current, so it will sense the current. Automatically the voltage there will change. That will trigger the gate circuit, that will initiate the gate circuit, and gate circuit will trigger crowbar thyristor will get shorted, and it will bypass this power converter and protects it. So this is about crowbar protection. Next is gate protection. So here the overall circuit is shown here. You have overcurrent protection. There is circuit breakers can be used for current protection. You have fast acting current limiting fuse that can be used. Then you have DI by DT protection is given. Snubber circuit is for DV by DT protection. S, it's not HR, it is HS. Heat sinks are given for SCR protection. Similarly, gate protection is also there. Gate should also be protected. So current to limit current, for gate current, to limit the gate current, you put an R resistance here. To limit the voltage, high voltage the gate, you put a Zener diode here. The Zener diode is for clamping the voltage. That is high voltage cannot be given to this gate circuit. Then you have here RC circuit. RC circuit is given there, that is for removing the noise. It's a low pass filter there which removes the noise, and you have to see that the capacitor value, C1 capacitor value which you choose should not be so high also. It should be a lower value, otherwise what will happen, the gate's signal, it will clamp the gate signal, and proper gate signals will not get in the gate. And even for removing the noise, say I said these converters come as a bank. So what will happen then, when the nearby thyristors are fired, automatically this thyristor will also get fired. So some due to electromagnetic interference may also occur, noise may be there. So to avoid that, what we do, we will shielded cables can be given near the gate, or twisted cables can be used in order to avoid false triggering in case of gate. So this is gate protection circuit. Next we go for thyristor commutation circuit. So the last circuit is the commutation circuit which is required for thyristor. Well, why is this commutation required? What does it need? What is commutation?
Turn off.
Turn off the thyristor. That is required, is it? Whenever we require, we have to turn off the thyristor. Many circuits, if you see, you have to turn off the thyristor. For example, you take an AC to AC converter. You use a cycloconverter for switching up the frequency. For in one cycle itself, you require more number of cycles. What you do? You turn on and turn off the thyristor in the same cycle. So for that purpose, what do you require? You require force commutation. You have to forcefully turn off the thyristor and forcefully turn on the thyristor. Can you tell some commutation circuit? In circuits where commutation is not required, natural commutation, the circuit which undergoes natural commutation, अपने आप where commutate होगा. Which circuits you don't require commutation? Circuits. Natural commutation it undergoes. That is a firing circuit. I'm asking in which circuit, like say DC to DC converter, choppers or inverters or rectifier, where commutation is not required. Say rectifier you take. When you take a rectifier, the input is AC. Okay, so automatically when the AC supply goes zero, it gets turned off. That is natural commutation. So wherever the input, say for AC to AC also, when it is a step down cycloconverter, में natural commutation, you will be seeing the step down and step down cycloconverters in the future when drives when we see. So there also you undergo natural commutation. You don't require force commutation. But in case of say DC chopper, where you want to convert DC to DC, there you go for force commutation. Okay, so some circuits where you go have DC, say inverter circuit, DC is the input and you get AC output. There also you require force commutation. So wherever the input is DC, you go for force commutation, and wherever the input is AC, you go for natural commutation. So commutation is a process of turning off a conducting thyristor. You have two types, that is natural commutation and force commutation. In force commutation again, current commutation is there and voltage commutation is there. So natural commutation, as I already told you, you can see here, this is the AC supply and the thyristor is being supplied with an AC supply. So when it crosses zero, zero crossing is shown here. So when zero crossing, automatically what happens? Turned off. Copper circuit or inverter, where the input is DC. Such cases we go for force commutation. Commutation achieved by reverse biasing the SCR. So force commutation, how it is achieved? We use inductors and capacitors and we reverse bias the thyristor or give reverse pulse to the thyristor. We give current opposite to the thyristor and we discharge the thyristor. That is how we do force commutation. So methods of force commutation you can see here. Methods of next slide. Methods of force commutation. You have load commutation. The load we use, say an RC circuit and RLC circuit, which we use a resonating circuit. That if it is a resonating circuit, automatically the current will cross zero and automatically it can turn. That is load commutation. Resonance pulse commutation is there. Complementary commutation, impulse commutation, external pulse commutation. These are the different methods of force commutation techniques. Okay. So force commutation is applied to chopper or inverters. Okay. So that is the load self commutation or a load commutation. So that circuit is, you can see here. Here we have used an RLC circuit. So RLC circuit, what will happen? The current will be a resonating one. So automatically when the current crosses zero, what will happen? It will commutate the thyristor. So you can see the characteristics here, and the current is, when the current of the circuit goes to zero, what will happen? The voltage across the capacitor is maximum. Okay, so the previous slide you can see here, this capacitor is connected across this thyristor. That capacitor voltage comes across this thyristor, and that is a reverse voltage is applied across the SCR. A reverse voltage comes across the SCR, so the thyristor gets turned off. Okay, so this is load commutation. Next is resonance pulse commutation. Resonance pulse commutation, or you can say this as current commutation. This is resonance pulse commutation. In this, initially let us say T1 is off and T3 is off, and we are turning on the supply. What will happen? The capacitor will start charging as shown here, plus in the left hand side and negative in the right hand side. So it gets charged. When it is fully charged, what will happen? It becomes open, and that voltage V comes across this capacitor. Now the capacitor is fully charged and the voltage across that is V. Now what happens? Now let us say that the thyristor T1 is on and it is conducting. We wanted to operate a thyristor. The thyristor is fired and it is operating here. Okay, it is operating continuously. Now we want to commutate this thyristor T1. Now my main thyristor is T1. Now we want to commutate this thyristor T1. So what you have to do? We have to just commutate this auxiliary thyristor. T3 has to be turned on. So now when I give a pulse to this T3, automatically what will happen? This circuit C, L and this T3 will form a resonating circuit. And now the capacitor will start discharging. So what will happen? This capacitor will discharge to T3 and L, and this forms a resonating circuit. And this capacitor will start charging in the opposite direction. This N, the right hand side N where it is negative will become positive, and this negative positive side will become negative, and it starts charging in the opposite direction. In one particular time, what will happen? This minus point will become plus, and this negative will become, this positive will become minus. So now this positive of this capacitor is across this cathode of T3. Okay, so what will happen? This capacitor will give a reverse bias across this T3. So T3 will automatically get turned off because of this reverse bias of this capacitor. This capacitor is reverse bias, and if this capacitor will reverse bias this capacitor will reverse bias this T3, and the T3 will get turned off. Now when T3 is turned off, what will happen? This capacitor with positive terminal at the right hand side will start discharging through CL, this diode, and T1. This will form as a resonating circuit. This small circuit will become as a resonating circuit, and automatically this capacitor will start discharging. So this pulse, current pulse, which is discharged, will go against this load current which is being delivered by this thyristor T1. So what will happen? The thyristor's current will start decreasing, and this current pulse will go across it. And one particular end, the thyristor current will become happen, thyristor will get turned off. This is due to current commutation. Okay, thyristor will get turned off, and now again the current will start flowing through this capacitor through the load. Okay, until this capacitor will get blocked. Like when it becomes fully charged, automatically it will get turned off. So this is how we commutate this thyristor T1. So this is a circuit given. Next is a complementary commutation. In complementary commutation, say thyristor T1 is on. Okay, so let us consider thyristor T1 is on. So voltage, this source which is connected gives supply through R2 and C and through thyristor T1. Now the voltage, this voltmeter, sorry, this voltage source which is connected gives current through R2, C and thyristor, and similarly through R1 also. Okay, so current is flowing through this, and thyristor T2 is off now. So what will happen to this capacitor? Capacitor will get charged with the right hand side with positive. This right hand side will be positive, and this left hand side will be negative. Okay, so now it is getting fully charged. In one particular end, this capacitor will get fully charged, so it becomes open, and there will be no current flowing through R2. Okay, so that time what is the charge? If you see, this right hand side is positive, and the left hand side is negative. So this positive at the right hand side is now, since it is open, just you can see here, this thyristor T1 is conducting. Since thyristor T1 is conducting, this what is the voltage across T2? That is the voltage which is across capacitor, because this point, this right hand side is positive, that comes across the anode of this thyristor, and this left hand side is negative. This left hand side is negative, and since this is short, that comes across T2. Okay, this T2 ka anode ke across negative and this. So this is now forward bias. So anytime you can give the pulse to the T2 will get turned on. Okay, now it is in that state. So whenever you want to commutate this T1, thyristor T1, whenever you want to commutate, what we do? We give a pulse to this T2 because it is already forward biased by this capacitor C. So now when you give a pulse, what will happen? This will get shorted. Okay, and when this is when you give a pulse to this, this gets shorted, and here the capacitor which is positive plate right hand side comes across this T1, and this negative will come across the anode of this. So this thyristor T1 is reverse biased. So thyristor T1 is reverse biased, and this thyristor T2 will get turned on. Okay, thyristor T1 is turned on, and we turn off. So this is complementary. Same way, when you want to turn off T2, we will turn on T1, because this capacitor again will start charging through R1 in this direction with positive in the left hand side of the capacitor and negative in the right hand side. So this process will continue. So whenever you want to turn off T2, what we do? We turn on T1. This is complementary firing. That is shown here. Next is external pulse commutation. External pulse commutation is using an external circuit, you can commutate this T1. This is our main thyristor T1 which we have to commutate. So we use an external circuit that is shown here, T3L, capacitor and an auxiliary voltage source. So with this auxiliary voltage source, thyristor and inductor, what will happen when thyristor T3 is turned on? This circuit will get turned on, this becomes a resonating circuit, and this capacitor which is shown here will get charged to 2 times V auxiliary because of this inductor. Inductor is also there, so inductor will get have some voltage across it. So this capacitor will get charged to 2 V auxiliary. So when this voltage becomes 2 V auxiliary, automatically this thyristor has a reverse bias across it, which is 2 VAC. So it's plus here, and this is a minus, and this voltage, if it is removed also, there is 2 VAC minus VAC, 2 V auxiliary and minus V auxiliary. Again a V auxiliary is there which is reverse across T3. So this T3 will get commutated. This is off. Now 2 V auxiliary is there across the capacitor. So now whenever you want to turn off the thyristor T1, what we do, we give a firing pulse to T2. So when we give a firing pulse to T2, this becomes short here. So this Vs and 2V auxiliary comes across this T1. So when this 2V auxiliary minus this Vs, that voltage comes across this, it will be a negative voltage which will reverse bias this thyristor T1. Automatically the thyristor T1 will get turned off. Okay, so this is also an external means by which you can turn off the thyristor. So in all the commutation circuit, you have to just remember one thing. What we do, we give a reverse voltage across the thyristor. That is what we do. When we give a reverse voltage, that we do it using capacitors or an inductive circuit, which we charge it opposite to the thyristor which is present and just connect it to it. Automatically, we can turn it off. So we have voltage commutation circuits, current commutation circuits. We have auxiliary commutation circuits, load commutation circuits. Even you have natural commutation circuits. Natural in the sense automatically when you give AC supply, it gets commutated. So these are the different commutation circuits present. You have triacs. Triacs, as you all know, it is a bidirectional device. Okay, it is just like a diode, but diode two diodes connected in anti-parallels or two SCRs connected in anti-parallels, just like that, which you can see here. MT1 is one of the terminal, MT2 is one of the terminal, and G is thing. So just like a diode, diac is two diodes connected in anti-parallel. When it is a triac, it is two SCRs, or you can say two thyristors connected in anti-parallel. Thyristor is a common name for SCR. Okay, SCRs, two SCRs connected in anti-parallel. So here, 4 quadrant operations are possible because bidirectional. But mostly this triac, you make them operate in quadrant 1 or quadrant 3 operations. So now I am not going into the operation because of the shortage of time. So just triac also it is for bidirectional device. Just remember that. So here it is shown for each quadrant operation what is the different polarities of gate you have to give, and the MT2 terminal or MT1 terminal in which quadrant, like for say first quadrant operation, you have to keep MT2 positive, MT2 positive and gate positive. Since MT2 positive and gate positive, you get first quadrant operation. When gate is negative, which is shown here, gate is negative and MT2 is positive, you get second quadrant operation. Similarly, the other things are also given. Mostly the first and the third quadrant operations are used here. So here triac characteristics is given. Similar to the SCR, only thing is third quadrant also you can operate that. Okay, so that is VI characteristics. And here you can see here using the gating circuits, in the AC positive half cycle also you can control the firing angle. So you can control it. Similarly, in the negative half cycle also you can control it when you are connecting two SCRs in anti-parallel or using a triac. So here we will be seeing we have a hardware section also. So when we do that session, you will understand it. Okay, so these are the operations. I am leaving it because of lack of time. So here even a lamp dimmer. This circuit, like thing with SCR, we will be doing in the lab. This is a lamp dimmer where SCR firing is done using a diac and a resistor. So this circuit, so a similar circuit for drive control, we will be doing it. It's shown here. These are the circuits which are shown. And similarly, similar to thyristors, we can also use MOSFETs, BJTs, and IGBTs also. Okay, those are also used for drive application. We'll just see the different comparison. With that, I will be just leaving the session, and afternoon we will reassemble. So first of all, comparison of MOSFET and BJT. You can see MOSFET is a unipolar device. Okay, MOSFET is a unipolar. The majority carriers, whichever is the majority carrier, it operates with that. And BJT, if you see, it is a bipolar. Both holes and electrons contribute to the current there. And MOSFET is a high input impedance. It has high input impedance, and BJT has low input impedance. And MOSFETs, if you see, low switching losses. So it has low switching losses and conduction losses is more. So that's why for high switching frequency application, you go for MOSFETs. And BJT, if you see, It has high switching losses but low conduction losses. So for low switching frequency application, you go for BJT. And MOSFETs, it's voltage control device, and BJT, if you see, it's a current control device. And MOSFETs, it is having positive temperature coefficient of resistance. Okay, that is, when the temperature increases, its resistance also increases. But in case of a BJT, when temperature increases, the resistance decreases there. So that is the thing in case of BJT and MOSFET. Since MOSFET has a positive temperature coefficient of resistance, parallel operation is easy in MOSFET. Because what will happen when the temperature is increasing, here resistance is also increasing, so automatically current will be bypassed through other parallel devices which are connected. So parallel operation is possible in MOSFET. And in case of MOSFET, secondary breakdown does not occur. Okay, in case of BJT, secondary breakdown occurs. That is a disadvantage of BJT. See, the advantages and disadvantages of these things are combined. Like say, all the disadvantages are overcome and all the advantages are taken in case of IGBT. So IGBT is a device where all the advantages of MOSFETs and the advantages of BJT are combined and all the disadvantages are removed, and we go for a device that is called the IGBT, that is insulated gate bipolar transistor. Okay, insulated gate bipolar transistor, that is a device which combines the best qualities of both BJTs and MOSFET, and all the best qualities, like say IGBT possess high input impedance like MOSFET and low on-state power loss. When it is on also, power losses come in case of BJT, and high switching frequency also it has more or less similar to that of MOSFET. So for high switching frequency application also you can go, it can remain in on state and has high input impedance. Then another thing is it's free from secondary breakdown problem which is present in BJT. So mostly we go for IGBTs for firing. So mostly in the control of drives, we go for MOSFETs or IGBTs or even thyristors. Okay, so this is about this, and this session we'll stop here. And after lunch, we will again reassemble for MATLAB based control of drives. So now in this in the afternoon session, you can just sit here, and I'll have given a practice session in tomorrow afternoon for MATLAB. So you can sit here, listen to it, you can note down. We will go step by step very slowly, and we will see the MATLAB portion, because MATLAB simulating is very required. Drives, when you go for drive circuits, I'll be showing some drive. There you require some basic concepts about MATLAB simulating. So that we will be covering in the afternoon section. MATLAB simulating will be covered. There you can see. Okay, you need not work with MATLAB. That we will work tomorrow. Again, I'll be repeating it tomorrow also, so you can work there, and whenever you have some problem, you can ask then and there. So now in the afternoon session, we will just go through MATLAB, and we will again reassemble at 2 o'clock. Almost those who are connecting the centers, please come at 2. Others at 2:15 the lunch. 1 hour I'm giving. You can just go and come back, and again in the afternoon we will restart. And now I just want to talk with these centers, whether they have listened or they had some problem. First, which center, sir? Which center you connect? St. Joseph College.
Yes,
St.
ma'am.
Joseph College. Anyone is there with St. Joseph College?
Yes, ma'am.
Did you hear the session? Was there any problem?
Yes, ma'am.
Was there any
No,
problem
ma'am.
in hearing? No, you
Some
heard it.
interruption in the
In the
sound.
afternoon, we'll again read. What's up?
There are some interruption in the sound.
Okay. So there was some interruption in sound. It was not clear then.
It is 90% clear.
Okay. So anyway, we'll again check out in case higher bandwidth कुछ connect कर सकते तो again we'll try to do it.
Okay.
But in the afternoon again we will meet. Okay, at 2 o'clock, and MATLAB.
Okay.
We will start with MATLAB basics. I'll be explaining. Okay, sir.
Okay,
And
ma'am.
if you have any problem, you can just call me in the mobile also, and you can stop then and there.
Okay,
In case
ma'am.
if you can't. Okay. So So now we can leave for
Okay.
lunch.
Okay, thank you, ma'am.
So the next, okay. Next center. Which center is this? Register. DRA college. DRA They're online. Was there any problem? Can again come back? DRA group of institutes. DRA group of institutes. Can you hear? Sunrise group of institutes. Sunrise group of institutes. Can you hear me? आपका mic mute है mic. Your mic is mute.
Unmute your mic.
Unmute it.
Okay.
The mic. My audio is clear enough. Was it clear? Any problem with hearing?
I can listen you, but the clarity is a problem. Voice clarity is not there.
Okay, clarity is not there.
Yes.
Voice
Sir, no.
afternoon in case there's any problem, please stop then and there.
Okay.
Yes, make it in the afternoon.
Madam, some settings are disturbed at the end.
Hello?
Hello, madam, some settings are disturbed at your end.
Sunrise?
At your system. Some settings are disturbed at your system.
आपका स्पीकर को आप थोड़ा दूर रखो माइक से ना. स्पीकर को इको नहीं आएगा. From your side.
Can you hear us clearly? उनका माइक का तो प्रॉब्लम नहीं है.
आपका माइक म्यूट हो गया है.
उनका स्पीकर का तो प्रॉब्लम नहीं है.
शायद इको होगा उनका. इको आ रहा है उनका.
What about the other centers?
आपका माइक म्यूट हो गया है.
म्यूट अनम्यूट हो रहा है आपकी तरफ से.
And देख लेना कि आपका स्पीकर का तो प्रॉब्लम नहीं है. देख लेना. Because other centers they are saying 95% it is clear they are saying.
स्पीकर को थोड़ा दूर रखना है. इको नहीं आएगा.
Okay, other centers. What about the other centers? Okay, so thank you. We'll again meet at 2 o'clock. Lunch करके आ जाना. Other कौन सा है? सब चले गए.
चले गए.
Okay, फिर तो. And afternoon में इनको बोलना है.
Yes, you're audible.
In case सर आपका स्क्रीन में से चेक कर लेना. स्पीकर का भी प्रॉब्लम हो सकता है. The other centers they are saying it is clear only. स्पीकर में प्रॉब्लम नहीं है.
मैडम ये शुरू के हाफ एन आवर सही चलता है, फिर नेक्स्ट हाफ एन आवर डिस्टर्ब होता है, फिर वापस सही चलता है, फिर डिस्टर्ब होता है. इसलिए माइक सेटिंग्स बिल्कुल परफेक्ट करके किया हमारा इंजीनियर. तो बोलो
माइक थोड़ा
माइक को
पीछे लग जाए. माइक keep your mic away.
मैडम इतना दूर रखा हुआ देखिए.
Now speak.
नाउ
Yeah.
See, the voice is continuous. Sometimes it goes up, sometimes there is no sound.
Okay, okay. I have a problem. Anyway, we'll talk with our technical person and we'll tell it. The afternoon session, we will see that it is clear. Yes, sir.
I could not understand
Okay,
what
I'm
you are saying.
telling them.
Okay, ma'am. After that.
Okay, sir. Okay, thank
Okay, thank you, madam.
लॉक करके जा रहे हैं ना इसका रूम का की है
हमारे पास
लॉक करके चले जाएंगे
लॉक करके जाओ।
आप लोगों के लिए भी जाएंगे हम कोई सॉरी इतना
एक तो पहले से इधर बहुत दिक्कत थी, नेट नहीं चल रहा, फिर बैंडविड्थ नहीं हुई।
अभी ना हम कनेक्ट डिस्कनेक्ट करके अगेन कनेक्ट किया तो और भी प्रॉब्लम हो रहा है
इसको वही कर हमारे वाला सेंटर आ जाएगा। चलो क्या कर रहा है, खाना खा ले बड़ा। ये अल्फाबेट क्या क्या पता चल रहा है?
लैग होता है।
कर सकते हैं अभी लंच के